Welcome back. In this video, we'll consider the Cauchy's second integral theorem. This is also sometimes called the Cauchy's Integral Formula. Now, in our last video, we had already considered extensively the Cauchy's first integral theorem, and we saw how it worked. Now, let's do the same for the Cauchy's second integral theorem. As always, make sure to like, share, and subscribe, and turn on notifications so you don't miss any of our videos. Let's begin. First, the statement of the Cauchy integral formula. Let f of z be a single-valued and analytic function throughout a simply connected region R. Let C be any contour interior to R and enclosing Z0, with Z0 being an isolated singular point of the integrand f of z divided by z minus Z0. Then, f of Z0 is equal to 1 over 2 pi I integral over C f of z divided by z minus Z0 to z. Now, let us pick out the most important information within this theorem. Of course, the conclusion is to prove this integral. However, there is a lot of information in the premise. The very first thing is that the function is single-valued and analytic. The function is analytic throughout the simply connected region R. Now, the function is bounded by a contour that is interior to R. Now, this contour is enclosing Z0, which turns out to be an isolated singular point of an integrand. Now, being an isolated singular point means you are a point of discontinuity that can be extracted from the function in order to make the entire function continuous in every other place. This is what it means to be an isolated singular point. It could also be referred to as a hole, and in some cases as a pole as well. We'll look at those namings further later in the series. Now, if this is the case, and we have C as a contour inferior to R and enclosing Z0, which is an isolated singular point, it means that what we have on our hand now is a doubly connected region. Now, what is a doubly connected region? Remember, a doubly connected region is simply a region that is connected and has exactly one hole or one isolated singular point, which means you can shrink the region to a point without crossing that hole, right? But then there's just one hole in that regard. So the goal of this, in order to utilize the fact that f of z is single-valued and analytic throughout a simply connected region, what it means is that we would have no choice but to find a way of recreating this doubly connected region C as a simply connected region by removing or by extracting out this isolated singular point. Now, how can we do this, or how can we isolate it? We would be doing that using what is referred to as a cross-cut. Now, I will try to provide a diagrammatic representation of this so that we have an idea of where we are going to based off this question or this theorem. So, of course, as always, let's start first and foremost with the cogent proof that the cogent premise that we need to proceed, right? F of z is single-valued and analytic throughout a simply connected region. Now, for this region, we have a contour C that is completely interior to R and enclosing Z0, which is, of course, an isolated singular point. Now, let's give a representation of what the current doubly connected region would look like. Now, remember, this is not a very accurate sketch, but we'll try as much as possible to make it so. So we have, of course, we have the outer region, and then we have the inner region. So think about it as if, remember when you have like a disc. Remember all those discs we can put into CD drives, and you realize that there's a hole in the middle of the CD drive, and then there's the outer core, right? So that CD drive represents a doubly connected region, right, which has exactly one hole in the middle of it, right? If you have a plain disk with no holes, then you have a simply connected region, right? A good example is if you're talking about the cover of your milk tins or your paint buckets and the round covers. Those are simply connected regions, right? But if you have a CD drive which has a hole in the middle, then that's a good example of this doubly connected region. Now, I can create, of course, within this doubly connected region is where I would have Z naught, and I can create within that Z naught a radius A around that Z naught, where Z naught now becomes the center of that inner contour, right? I want to check that inner contour as C1 and then this outer contour as C, right? So I have created this inner contour C1 around Z naught. Of course, we'll make some namings, some standard namings as we begin writing. Now, this is a doubly connected region as it is because it has a hole in the middle, which is, of course, around Z naught. However, this doubly connected region can be created as a simply connected region by introducing what we refer to as a cross-cut of infinitesimal width. Infinitesimal width means that that cross-cut is so minute that if you do not observe closely, you feel like, in fact, there is no cut in the middle at all. But what that cut will do is, because we realize that it is a doubly connected region, so there is no connection between the inner circle and the outer circle, but that cross cut will link those two together in such a way that by the time they are linked, like so, right? Of course, the cross cut will be so small that it will not even be this visible, but we need it to be at least this visible so that you can see what's going on. But what you will notice is that by this cross cut, you have now created a simply connected region because you now have a curve that starts from one point and moves back to that point without any breakages because you have connected the inner and the outer regions together with this cross cut of infinitesimal width. We say infinitesimal width so that the distance between the cuts is so small that it's as if there was no cut at all. A good example is if you take a plain paper like this one I'm using for this video, and then you cut it in a circular shape, right? And then you punch a hole in the middle, right? So you know you have created a doubly connected region like that. And then you now take a scissors. The scissors will even create a large hole. You now take a blade and then you now go from the middle you have punched the hole and you just draw that blade to the end of your circular shaped paper. What have you noticed? Because you use the blade which is so thin, you realize that the moment you take the blade off the paper, if you place the paper silently or flatly on the plain surface, you would not even notice that there is a cut there. However, the cut has been made such that there is now a fully flowing line that goes to the hole and back to the front and then continues without any stoppages, thereby creating for you a simply connected region. I hope this makes a lot of sense for us. So let's now define what happens within this circle, right? So let C1 be the inner contour with, of course, center Z naught and radius A, right? So this, of course, makes it a simply connected region. Of course, do not also forget that by the Cauchy's first integral theorem, remember, by the Cauchy's first integral theorem, where we have already said that all the first derivatives are continuous, right? By the first integral theorem, since we have created a simply connected region now, we know that the integral over C of rho of Z, the Z, would be equal to the integral over C1, which is the newly created contour, on that same function, rho of Z. Now, what exactly is rho of z? Rho of z is the function on which z not exists as an isolated singular point, which is this. So where rho of z equals f of z over z minus z naught. Right? So we are beginning to piece all the information we need together. Now let us see what happens. Right? Where z is of course any arbitrary point within this contour C1, which means whatever happens on C1 totally tallies with what happens on C. Right? Now, of course, if you take the difference between any of the complex variables within this contour and the center C Z naught, you would have yourself a complex number, right? Now we can write this complex number as a complex variable, correct? Now if we write it as a complex variable, what would we have? Remember that we have simply said that A, of course, is our inner radius in this case. Now, if we have this as an inner radius, remember that A will be very, very small because we want this to be as small as possible, right? So that it is making it even easier to isolate that singular point. Now, if this is the case, we can have z minus z naught representable as the complex number A e raised to power I theta, where A is, of course, the radius and theta is the angle around the center, right? Based off this, we can write z as subject of the formula. You have z naught plus a e raised to power I theta, and then we can go ahead to differentiate z to have, remember that z naught is the center, which means the value we know is a fixed value to be a constant value. Differentiation of a constant would of course give us 0, and so we'll be having I a e raised to power I theta left. This is what we're going to have left. Now, if we put all this together and we make our case into, of course, we make our case into the formula, right? We would simply have that the integral over C1 of rho of z dz will simply be the integral over C1. Now, remember, f of z, since z is written like this, we can rewrite z inside the function as f of z naught plus a e raised to power I theta, these two being powers, right? And then divided by z minus z naught, which is a e raised to power I theta, and then dz, which of course we are given as I a e raised to power I theta. There's all we go. So this cancels out. So we are going to be left with the integral over C1 f of z naught plus a e raised to power I theta I d theta. So we have been able to casually move away from a variable of z, which would have taken us to x and y, out and into a variable of theta, right? A and theta. Now, if we have this representation, what exactly do we know? Remember that we have said that this radius A is going to be very, very, very small. It's going to be a very, very, very small radius. And if it's going to be a very, very small radius, it means that we are going to have it as small as possible. Even the cost cut is of infinitesimal width, so the radius also has to be as small as possible. So if the radius is going to be as small as possible, we want to consider what happens as we take that radius as close as possible to 0. Does that make sense? Now, let's put all of this into consideration and see what we have all at the same time. Now, remember that by the Cauchy's first integral theorem, we have said that the integral over C1 is the same thing as the integral over C. So from here, I can make my I can make my inference that this integral I have here over C1 is in fact going to be the integral over the entire C. Now, let's put that all together for a minute and see exactly what we would have. Now, the very first thing we'll do is this, of course, will now become the integral over C I f of z naught plus a e raised to power I theta d theta. Now, as a tends to 0, because a is very, very small, remember, this radius a of this inner circle is very, very small. So as a tends to 0, we see that if we take the limit of this function, we would have that the limit as a tends to 0 of integral over c, right, rho of z d z would be equal to I limit a tends to 0 of integral over c f of z naught plus a e raised to power I theta d theta, right? Now, do not also forget that since we are integrating now over the entire contour that has now become a simply connected region based off the cross cut of infinitesimal width that we introduced, then it means the integral over c is the same thing as the integral over the entire circle. So, as a tends to 0, this will vanish, and we would be left with I f of z naught integral from 0 to 2 pi of d theta. This is what we're going to have. And of course, if we have this, remember the limit would not have anything to do on the left-hand side. So it's just going to be integral over c, right, of rho z dz. That's what we're going to have. Now, if we take this and see exactly how to expand this, we would notice that, remember, rho z is equal to f of z over z naught, right? So if we put that into or return the value, it would mean that we have the integral over c of f of z divided by z minus z naught. The z would now be equal to I f of z naught, right? Theta, because the integration of d theta gives you theta. This goes from 0 to 2 pi. The lower limit will, of course, vanish, or the lower bound will vanish, and then, because it's at 0, and then the upper bound will exist, we'll have that to be 2 pi. That will be 2 pi I f of z naught. And then the left-hand side remains integral over c f of z divided by z minus z naught to z. So if we put that together, therefore, it means that if we make f of z naught solve the formula, we'll simply have 1 divided by 2 pi I integral over c f of z divided by z minus z naught to z. And that would complete the proof of the Cauchy's integral formula, or the Cauchy's second integral theorem. So what you would notice from here is, first and foremost, what is necessary is the understanding of the fact that because the contour contains an isolated singular point, it means that a hole is formed somewhere within that contour, thereby creating a doubly connected region. Now, if we have a doubly connected region, the very first thing we need to do is to recreate it as a simply connected region, because remember the premise tells us that f of z is single valued and analytic throughout a simply connected region. So we need to have a simply connected region. How do we have that simply connected region? We create this cross cut. This is a cross cut of infinitesimal width. So by creating this cross cut, we have ensured that, while ensuring that the difference between the cross cut is so small, and of course the hole in the middle is also so small as possible because the radius is as small as it can, we have connected the inner hole with the outer contour, thereby creating a simply connected region, which means you create a region such that if you start from a point, you can draw up to that point back without any breakages, right? That is very, very, very important, as the case is. And then from there, we then applied the kinds, the property of the complex number that will exist within the region, of course, and then we also rewrote it as an exponential form in order to solve the Cauchy's second integral theorem. I hope this was well taken and clear. If you have any questions, of course, do make sure to ask me in the comments. As always, make sure to like, share, and subscribe, and turn on your notifications to ensure that you do not miss any of our videos.